All right, get ready, everyone. We're diving into some seriously mind-bending physics today. Einstein's early work on light, specifically how it interacts with matter.
Sounds intense.
It is. You actually gave me a whole stack of his papers from the early 1900s, and wow, even for physics enthusiasts, this stuff's dense.
Oh, yeah, definitely a challenging read.
So we're going to break it down, right? Highlight those key aha moments, and trust me, there are some real gems in here.
I think what's so fascinating is how Einstein, even in these early papers, is connecting all these seemingly totally unrelated phenomena.
Right.
We're talking blackbody radiation, cathode rays, even photoluminescence.
Wow.
And he ties it all together with this like revolutionary idea of light as quantized packets of energy. It was a huge shift in how physicists were thinking back then.
Okay, so let's unpack this a bit. Yeah, starting with this blackbody radiation. I see Einstein really dives into the work of Max Planck here.
Yeah.
Can you give us kind of a quick rundown of what Planck was even proposing?
Absolutely. So Planck, he was wrestling with this problem of like how objects emit light when they're heated, right?
Yeah.
And he came up with this radical idea, like energy isn't emitted continuously, but in these tiny discrete packets that he called quanta.
Okay.
It's almost like saying energy comes in little bundles instead of this like smooth flow.
Okay, so energy comes in little bundles, like I guess like a vending machine dispensing snacks.
Yeah.
Instead of like a soda fountain or something. Okay, I gotta get that. So where does Einstein come into all of this?
So Einstein basically takes Planck's idea and runs with it. He uses it to analyze how light interacts with what he calls resonators.
Resonators.
These theoretical entities that can like absorb and emit light energy.
So these resonators, are they kind of like tiny antennas almost?
Exactly.
Tuned to specific light frequencies?
Yeah, exactly. And here's where it gets really interesting.
Okay.
Einstein then applies this whole quantized energy concept to explain something called the photoelectric effect.
The photoelectric effect. Now, I vaguely remember this from my physics class, but something about light knocking electrons out of metal.
That's it. It was this puzzle back then because classical physics couldn't really explain why certain frequencies of light could cause this effect while others couldn't, no matter how intense the light was. But Einstein, using Planck's quanta, he nails it. He says it's not the intensity of the light that matters, it's the energy of the individual light packets, which he later calls photons.
Okay.
It's like it takes a single bullet with enough energy to knock an electron out, not like a bunch of tiny pellets.
So light is acting like a stream of tiny bullets almost, and each bullet is a photon with a specific energy.
Yeah.
That's a wild way to think about light, right?
Yeah.
Because we usually think of it as a wave.
It is. It's a radical departure. And to make things even clearer, he comes up with this equation. It's E equals R beta nu over N. And it directly links the energy of light to the number of these elementary quanta involved in the interaction. Essentially, the equation is saying, hey, light itself is made up of these energy packets, photons.
Mind officially blown. But he doesn't stop there, right? I see he goes on to connect this to entropy and Boltzmann's principle. Now, entropy is basically a measure of disorder, right?
Exactly.
Like my desk after a long day of work, maybe.
Exactly. But what's groundbreaking here is how Einstein applies this concept of disorder or randomness to light itself.
Oh, okay.
He links the statistical interpretation of entropy to the volume occupied by light. Imagine a box filled with photons, right? The more those photons spread out and fill the box, the higher the entropy. It's like letting those papers on your desk scatter all over the place.
Okay, so more space for the light to bounce around in means higher entropy,
Yeah.
more disorder. But why is that such a big deal?
It's huge because it suggests that light, which we typically think of as this continuous wave, can actually be analyzed statistically.
Really?
Like a bunch of individual particles. It's like saying that even though light has these wave-like properties, at a fundamental level, it's also granular, like a gas made up of tiny particles.
So we're saying that light can behave like both a wave and a collection of particles?
Precisely.
That's some serious wave-particle duality.
Yes. And this really sets the stage for understanding things like the Stokes shift.
Okay, the Stokes shift. Now, refresh my memory on that one. What was that all about?
So imagine shining a light on certain materials, right?
Okay.
They absorb that light, and then they re-emit it. But the emitted light, it's often a different color. It's shifted towards a longer wavelength, meaning it carries less energy. Einstein links this directly back to the quantized nature of light. He's saying that some energy is lost during the interaction with the material, causing the shift.
So it's like the material absorbs a high-energy photon, then spits out a lower energy one, causing that color change.
Exactly.
Interesting.
And this seemingly simple phenomenon has huge implications in fields like fluorescence microscopy and material science.
And I see he also connects this whole quantized light concept to cathode rays. Those beams of electrons were a hot topic back then.
They were.
Yeah.
And Einstein suggests that the energy carried by light can actually be transferred to electrons within a material, causing them to be ejected.
Oh, wow.
Just like in the photoelectric effect.
Interesting.
He's saying that light can literally kick electrons out of matter, creating those cathode rays. This was a major step towards understanding how light can be used to control, like, electrical currents, which led to inventions like, well, the television.
Wow, from blackbody radiation to cathode rays, all connected by this idea of quantized light.
It's pretty amazing, isn't it?
It is.
And we're just getting started. Einstein doesn't stop there. He dives into the ionization of gases, connecting it to...
Okay, hold on. Let's not get ahead of ourselves here. We've covered a lot of ground already, and I think our listeners could use a moment to process all this mind-blowing physics. We'll be back in a flash to continue our deep dive into Einstein's incredible work on light.
Welcome back, everyone. Before the break, we were talking about how Einstein used this idea of quantized light to explain all sorts of things.
Yeah, like blackbody radiation, the photoelectric effect. My head is still spinning a little.
I bet.
But I'm ready for more.
Okay, well, hold on tight, because Einstein's next move is to tackle the ionization of gases, and it's a doozy.
Okay, ionization of gases. For those of us who haven't taken a chemistry class lately, remind us what that even means.
Oh, right. So ionization is basically the process of an atom or a molecule gaining or losing electrons, which gives it a net electrical charge. Think of it like stripping away or adding these tiny particles to make something electrically active.
Okay, got it. So how does light even play into this? I mean, how can you shine light on a gas and cause it to become ionized?
Well, this is where Einstein's genius really shines through again. He uses his trusty quantized light idea to explain it.
Okay.
He proposes that if a photon, remember that's a packet of light energy, right?
Right.
If it hits a gas molecule with enough energy, it can actually knock an electron right off of the molecule.
So it's like a tiny game of billiards almost, with photons as the cue ball smashing into electrons and sending them flying.
That's a great analogy. And just like in the photoelectric effect, it's not the intensity of the light that matters.
Right.
It's the energy carried by those individual photons.
Right. Okay.
If a photon doesn't have enough energy to overcome that binding force holding the electron to the molecule, nothing happens.
Okay.
But if it does, bam, ionization occurs.
It's kind of like trying to break a twig or something, right?
Yeah.
If you apply enough force, it snaps, but if you don't, it just stays intact.
Exactly. And Einstein, being the incredible physicist that he was, he actually went on to develop the simple but really elegant equation to describe this whole process. It goes like this. R beta nu is greater than or equal to J, where R beta nu represents that energy of the light quantum, and J is that ionization energy of the gas molecule.
Okay, that equation, it might look a little intimidating to some people. Can you break it down for us non-physicists? What is it really telling us?
Sure. In simple terms, what the equation is saying is, for ionization to occur, the energy of that incoming light, that's the R beta nu, has to be greater than or equal to the energy holding that electron to the molecule. The ionization energy, that's the J.
So if the light's energy isn't high enough, no ionization. But if it is, game on.
You got it. And this equation actually has some pretty profound implications. It means that scientists can use light to control, like, chemical reactions, create plasmals, that superheated state of matter.
Wow.
And even study, like, the composition of stars.
So from something as seemingly simple as just shining light on a gas, we get insights into, like, the inner workings of stars.
It really is. But remember earlier we were also talking about how Einstein linked entropy to the volume of light.
Right.
He went deeper into that connection, and he actually came up with this statistical interpretation of entropy for radiation.
Okay, back to entropy. I'm still trying to wrap my head around how light, something we usually think of as continuous, can be described using this concept of, like, disorder.
It is a bit of a head-scratcher. But think of it this way. Imagine a bunch of photons bouncing around inside a box.
Oh.
The more ways those photons can be arranged within that box, the higher the entropy. It's like having a deck of cards, right? The more you shuffle them, the more disordered they become.
Okay, so the more possibilities for arranging those photons, the higher the entropy. I think I'm starting to get it.
Good.
But what does this have to do with Boltzmann's principle?
Ah, great question. So Boltzmann's principle, it relates entropy to the number of possible microstates of a system. A microstate is simply a specific arrangement of all the particles in that system.
Okay.
Boltzmann's principle basically says that the entropy of a system is proportional to the logarithm of the number of possible microstates.
Okay, that's a mouthful. Can you give us like a real-world example?
Sure. Imagine like a room with 10 coins scattered on the floor.
Okay.
There are tons of ways those coins could be arranged, right? Heads up, some heads, some tails.
Yeah.
Each one of those arrangements is a microstate. The more possible microstates, the more disordered that system is, and the higher its entropy.
So a room with coins scattered everywhere has higher entropy than a room with all the coins neatly stacked in a pile.
Exactly. And Einstein applied the same logic to light. He said that the entropy of a volume of light is related to the number of ways those photons can be arranged within that volume. The more ways they can be arranged, the higher the entropy.
So it's like those coins again, but instead of coins, we have photons bouncing around. The more spread out and randomly arranged they are, the higher the entropy of the light.
Precisely. And the statistical interpretation of entropy, it has far-reaching implications in physics.
Really?
From understanding the behavior of, like, black holes to developing new technologies like lasers.
Wow, who knew disorder could be so powerful?
Right. And remember, earlier we touched on the Stokes shift,
Yeah.
where the re-emitted light has that longer wavelength and less energy than the absorbed light.
Right.
Well, guess what? Einstein connected this to the quantized nature of light and the concept of entropy, too.
Wait, really? How does that work? It seems like we're connecting like a whole bunch of dots here.
We are, and that's the beauty of Einstein's work. He saw connections where others didn't. Here's the gist. When a material absorbs a photon, it gets bumped up to a higher energy level, kind of like climbing a ladder.
Okay.
But this excited state is unstable, so the material wants to return to its ground state. That's like the bottom of the ladder. To do this, it emits a photon, but some energy is lost in the process, maybe as like vibrations within the material. This energy loss means that the emitted photon has less energy, hence that longer wavelength. That's the Stokes shift.
So it's like climbing a ladder and then sliding down a slide.
Yeah.
You end up lower than where you started
Yeah.
because some energy is lost due to friction.
That's a perfect analogy.
Okay.
And this energy loss is a way of increasing entropy. Remember, systems tend towards disorder.
Right.
And the Stokes shift is like a prime example of this principle in action.
Wow. So the seemingly simple phenomenon of a color change when light interacts with matter is actually a manifestation of entropy at work. That's deep.
It is. And it highlights how seemingly disparate concepts like light and energy and entropy are all interconnected in this like grand dance of the universe.
Okay, I need a moment to let all of that sink in.
Yeah.
But before we do, let's circle back to those fascinating cathode rays. I know Einstein had some pretty important insights about those as well.
Absolutely. He was particularly interested in like how these beams of electrons, cathode rays, could be generated using light.
Right.
And his explanation, once again, relied on this quantized nature of light.
Okay, remind me again how cathode rays are even formed. I remember something about a beam of electrons, but the details are a little fuzzy.
Sure. Cathode rays are essentially streams of electrons emitted from a negatively charged electrode, called a cathode, in a vacuum tube.
Okay.
These beams were a hot topic in the early 20th century because they revealed a lot about the nature of electricity and matter.
Right, and I think I remember that they were also crucial for like developing some pretty important technologies, right? Like
Yes.
television.
Exactly. Cathode ray tubes, or CRTs, were like the backbone of televisions and computer monitors for decades.
Wow.
But back to Einstein, he proposed that light could actually be used to generate these cathode rays
Really?
through a process very similar to the photoelectric effect.
Wait, so he was saying that shining light on certain materials could actually cause them to emit these beams of electrons.
That's precisely it. He hypothesized that if a photon with enough energy strikes a material, it can transfer its energy to an electron within that material, giving it enough energy to escape and become part of a cathode ray.
So it's like the photoelectric effect, but instead of just knocking an electron loose, it's giving it enough energy to join a whole beam of electrons.
Exactly. And what's even more remarkable is that he didn't stop at this qualitative description.
Really?
He went on to develop mathematical equations to describe, like, the energy distribution of these emitted electrons. relating it to the frequency of the incident light.
So he was able to quantify this phenomenon, not just describe it in words.
Precisely. His equations showed that the energy of those emitted electrons depends directly on the frequency of the light, just like in the photoelectric effect. This was a huge step forward in understanding how light can interact with matter to produce electrical currents.
So it sounds like we're seeing a recurring theme here. Einstein is taking these seemingly totally different phenomena.
Yeah.
Blackbody radiation, the photoelectric effect, the ionization of gases, even cathode rays, and tying them all together through this concept of quantized light.
You're absolutely right, and this underscores the unifying power of great scientific theories.
Yeah.
Einstein's insights on light weren't just about explaining these individual phenomena,
Right.
They were about revealing this deeper underlying connection between light, energy, and matter.
This has been one incredible deep dive so far.
Yeah.
We've covered so much ground, from the nitty-gritty of quantized energy to the grand implications of entropy and the Stokes shift. But I have a feeling there's still more to uncover.
Oh, yeah.
What other treasures are hidden within Einstein's work on light? Stay tuned for the final part of our episode, where we'll delve even deeper into the mind of a genius. Welcome back to our deep dive into Einstein's incredible work.
It's amazing, right? All this groundbreaking work.
Yeah, for sure. Stemmed from just a handful of papers from his miracle year, 1905.
Really makes you think about the power of one mind, huh?
It does. One mind to revolutionize how we understand the universe.
Yeah.
Pretty awesome. Before we wrap things up, there's one thing that's been on my mind throughout our whole discussion.
Oh, yeah. What's that?
It's this idea of resonators. Einstein keeps mentioning them.
Right, those fascinating theoretical entities.
Yeah, and to be honest, I'm still not totally clear on what they are exactly.
Yeah, they do play a pretty crucial role in how he explains light interacting with matter.
Exactly. Can you shed some light on that?
Absolutely. So remember how Einstein was trying to solve this problem, how matter absorbs and emits light, especially in blackbody radiation? He needed some way to model those atoms or molecules within a material, the ones actually interacting with light.
Okay, yeah, so like the tiny bits of matter that are actually absorbing and emitting those little packets of light energy.
Precisely. And that's where these resonators come in. Einstein imagined them as these tiny oscillators within the material, each one capable of vibrating at a specific frequency.
So almost like each atom or molecule is like a tiny tuning fork.
Exactly.
That can only vibrate at a certain pitch.
That's a great analogy. And Einstein proposed that these resonators could only absorb energy from light waves if the frequency of the light matched the resonator's natural frequency.
So it's like a resonance phenomenon. Like the light wave needs to hit the right note to make the resonator vibrate.
Precisely. Like pushing a swing, right? If you push at the right frequency, the swing goes higher and higher. But if you push at the wrong frequency, nothing really happens.
Okay, that makes sense. So the resonators are absorbing energy from light waves if they're tuned to the right frequency. Then what?
Well, when a resonator absorbs that energy, it gets excited, like the swing, going higher and higher. But eventually, like the swing slowing down, the resonator wants to get back to its ground state, that lowest energy level.
Right. So it has to get rid of that excess energy somehow.
Precisely. And it does that by emitting light waves at its own natural frequency, like the swing releasing energy as it slows down.
Huh. So these resonators, they're acting as both absorbers and emitters of light.
Yeah.
Tuned to these very specific frequencies.
That's right. And this model, these resonators, actually allowed Einstein to explain several key phenomena, including the photoelectric effect and blackbody radiation.
Okay, so let's connect the dots here. How do resonators help explain the photoelectric effect, where light is knocking electrons out of metal?
Well, remember how Einstein said light comes in those tiny energy packets, the photons?
Right.
He said a photon can actually transfer its energy to a resonator inside the metal.
So it's like a photon hitting that tiny tuning fork and making it vibrate like crazy.
Exactly. And if that photon has enough energy, it can make the resonator vibrate so strongly that it actually kicks an electron right out of the metal. That's the photoelectric effect in action.
It's like hitting the tuning fork so hard it breaks and a piece flies off.
You got it. And the energy of that emitted electron, it directly depends on the energy of that photon, which in turn depends on the frequency of the light.
Okay, that makes sense. Now, what about blackbody radiation? How do resonators play into that?
So remember Planck's law?
Yeah.
It describes the spectrum of blackbody radiation. the distribution of colors emitted by an object at a certain temperature. Well, Einstein actually used this model of resonators to derive Planck's law.
Oh, wow. So he actually explained one of the fundamental laws of physics using this idea of
He
resonators.
did. It was remarkable. He said that the resonators within a black body could only absorb or emit energy in those discrete packets, or quanta, which are proportional to the frequency of the light.
So basically, the energy levels of those resonators are also quantized, just like the energy of the light itself.
Exactly. And then by applying statistical mechanics to these quantized resonators, Einstein was able to reproduce Planck's law and actually explain that observed spectrum of black body radiation.
It's amazing how all these pieces fit together. It's like a giant puzzle, where each piece is some seemingly unrelated phenomenon, but Einstein found a way to connect them all. Through this revolutionary idea of quantized light and these fascinating resonators.
Yeah, it really is a testament to the power of theoretical physics and, of course, the brilliance of Einstein's mind. He didn't just explain individual things. He actually revealed this deeper underlying unity in how the universe works.
After this deep dive, I'm starting to see the world in a whole new light. No pun intended. It's like those resonators in our brains have been activated.
Uh-huh.
And we're now tuned in to this subtle symphony of energy and matter.
That's a beautiful way to put it. And for our listener, I hope this deep dive has sparked a sense of wonder and a desire to explore the mysteries of the universe even further, because who knows what incredible discoveries are still waiting out there.
Absolutely. This deep dive into Einstein's work has been truly illuminating. It reminds us that even the most complex ideas can be broken down and understood. And the pursuit of knowledge, it's a journey filled with awe and inspiration. So until next time, keep those minds curious and those imaginations firing.